Hello, welcome to your lesson on arithmetic sequences, a very big idea in mathematics. Let's listen closely. We're going to begin with a flashback, looking back at some concepts you've probably seen. So during this time, just listen, don't worry about taking notes quite yet. Alright, there are two key types of sequences we're going to look at. Today we're going to focus on arithmetic sequences. These are sequences with a common difference between successive terms. What that means is there's the same number added or subtracted between terms in a sequence. For example, here we can see this goes down by 2, down by 2, down by 2. So it's a common difference. So the next one's going to be 1, then -1, then -3. We call the common difference d, so that d value there is -2. In the next one, goes up by 1.5, up by 1.5 again, up by 1.5. Keep that pattern going, we have 9, 10.5, 12, and our common difference is 1.5. Those are arithmetic sequences. Let's look at graphing an arithmetic sequence. So here we have another one. This is the position number or term number. So term number 1 is 3, term number 2 is 7, and so on. Let's continue the sequence going. Looks like we're adding 4 every time. So 19, 23, and 27. Therefore, our common difference is 4. Again, this is our sequence given by u sub n, and this is position or term number. Graphing that, at position 1 we have 3, position 2, 7, position 3, 11. Let's graph all the points. I'm graphing the entire sequence. Again, position number is here, sequence values are here. Notice that arithmetic sequences are always linear. See how these line up in a linear fashion? That is true always for linear sequences or arithmetic sequences. Alright, so looking at these, decide which are arithmetic. Is this arithmetic? Let's check. Add 4, add 4. Oh, add 6 to get from 0 to 6. The difference is not common, therefore not arithmetic. Next one. Difference always 6 there, therefore arithmetic, and a d value of 6. This one, down 3, down 3, down 3, down 3 again. Yes, common difference of -3, arithmetic. This one, a little tougher. Think about how to find the common difference here. I'll give you a hint. Looking at the last one, to find this -3, well, of course it's obvious, but if you take the second value and subtract the first, so 14 minus 17 gives you that common difference. Also, third value minus second value, subtract gives you that. So if you subtract the next value, subtract the previous one from the next one, you'll always get the common difference. Let's see if that helps you with this one. Okay, so here I'm going to say the d value is u sub 2 minus u sub 1, so second term minus first term. And you can also find it by doing third term minus second term. These should match if you're looking at this one. The common differences should match if it's an arithmetic sequence. So second term, 6x minus 22 minus 3x minus 36, subtract that. Remember that this negative sign applies to both these pieces here. So you're going to end up with 3x minus 6. Let's try that with the u3 minus u2 as well. So 9x minus 28 minus 6x minus 22. That works out also to 3x minus 6. So the difference is common there. Maybe without calculating all that, you could have seen that also, because you can notice the x portion here goes up by 3x, goes up by 3x, and the numerical portion, -16, goes down -6, and then goes down -6 again. So you could have seen the 3x minus 6 just by looking at it that way. So it is arithmetic, and the d value is this. Alright, so now it's time to take some notes. You've been provided with a notes page for this section. Let's take notes on that. So let's define it again. Arithmetic sequences. Sequences that have a common difference are called arithmetic. Let's look at this sample problem. We have a geometric or visual pattern. Let's fill this table with the number of tiles in each figure. So figure 1 is going to be like our term 1, figure 2 is going to be term 2, and so on. So in figure 1 we have 1, 2, 3 tiles, 3. In figure 2, how many tiles is that? 5, and in figure 3, 7. We see a pattern established. It's going up by 2 every time. So it looks like it's arithmetic, so the next one will be 9. Alright, it's also important when we're making a rule to go back to what is called term number 0. Of course, term number 0 doesn't exist. We only have the first, second, third term. But if you see the pattern going up to, you can drop back to term 0 and say down to, so 1. That's going to help us understand where the rule comes from. So again, here's our position number on this axis, and over here we're going to have the value. So at position 0, we had that 1 there. At position 1, again, we have 3 tiles, 3. At position 2, or figure number 2, we have 5 tiles, and figure number 3, 7 tiles, figure number 4, 9 tiles. We can see it's arithmetic, we can see linear sequence of points there. And the rule, if you look at this just as a linear equation, well, you know the equation y equals mx plus b. Here is our y-intercept, our b value of 1, and the slope is rise 2 over 1, rise 2 over 1. So here's our linear equation for this. It would be 2x plus 1, y-intercept of 1, slope of 2. Now looking at it in terms of our language of sequences, our rule for sequences is going to be exactly the same, except we use the u sub n and an n here. So notice 2n plus 1, that they're identical. This is basically a linear rule. So arithmetic sequences, again, are linear rules. And notice that going back that one term gives us this value. So we can see this is going up by 2 every time, and there's our slope. And then when you go back to term number 0, which again doesn't exist, but you get the y-intercept value here. So it gives you that value there. So that's a quick and easy way to get a rule for an arithmetic sequence. Slope and go back 1 to the 0 term. Alright, try the same process with this one here. First, filling the table, we can see a pattern up by 2 every time. There's these tables, and you can see that every time you add a table, you add 2 seats. And the reason is, for example, when you put a new table here, it originally had 4 seats. 1 seat is blocked, but 3 are added. So it's like 4 minus 1 plus 3. That doesn't work. 1 seat is blocked, and 3 are added there. Yeah, that works out. Okay, so looking at that pattern there, we're going to make a rule. So plot the points, make a general rule. So here's plotting the points. We have these ones here. Again, we can go back to term number 0 as if there were 0 tables, which is not possible, but we can do that. These are going up by 2, so if you go back to term 0, you go down by 2. So 0, 2 will be our y-intercept. Therefore, there again is our linear equation. Slope of 2, y-intercept of 2, so 2x plus 2. Therefore, our general rule must match that linear pattern there. Again, you're looking at how much it's going by, so the common difference is the slope and the y-intercept here, which is a 0 term value. Great, now that you have the rule, you can find out what the answer to this question is. So you use your rule, you're looking for a 20th term, so u sub 20. You substitute 20 for the n, and you can calculate how many seats there will be for the 20th term, or 20 tables, and it's 42. Okay, let's do a quick investigation. Here we have this sequence, and what I'd like you to notice first is there a common difference? And there is. It's going up 3 every time. So we have a d value of 3 in this sequence. So maybe you already know what the rule is based on what we just talked about, but in this case I want you to try a little bit different things here. Write a recursive rule for u2 using d and u1. So remember, recursive rule will be u sub 2 equals and then something something with the u1 in that equation and the d's. Okay, here's a rule that works. To get the second one, because that's what this means, to get the second one, we take the first one and we add the d value to it. That makes sense. To get this one here, we took 2 and we added 3 to it. But here we're just using all symbols, right? We're going to keep this all symbolic here. Alright, try the same thing. Write a recursive rule for u3 using d and u1. So you may be tempted to use u2 and say, well, I'm jumping up 3 from u2, but try to keep using u1 in the equation. So you're making equations similar to this, but for u3. Okay, that equation is this. U sub 3 equals u sub 1 plus 2d. So notice, to get to the third one, if you begin at u1, you have to jump up once, twice the d value to get from u1 to u3. And that's what this is showing here. You add 2 times 3 to jump up to the third one. Okay, repeat for u4. That one is this. Alright, and this time from U1 you will jump 1, 2, 3 times, right? 3 D values. Again, 1, 2, 3 D values to get you to that fourth term. Alright, you see a pattern here, I hope, and we're going to use this pattern then to write a general rule. So what is the general rule for the sequence? And again, don't go back to the linear rule. Go for a rule that looks something like in this form here. So can you write a general rule? So this would be U sub n. And then what would it look like on this side? Okay, maybe you came up with this, and I hope that you did. We see to get any term, for example, the fourth term, we begin with the first term, and to it we add some number of d's, right? But the number of d, or differences we add, is always one less than the term we're looking for. For example, like we had here, we're looking for u4, but to get to u4 we only had to add 3 d values, because we only had to go 1, 2, 3 jumps to get from u1 to u4. So that jump number is always one less than the term we need, and that's what this is showing. N minus 1. We're doing one less than this. 3 is 1 less than 4, right? So there's our general rule. This is a key rule, one of the four or five key formulas in this unit. Please make sure to write that down on your page. There's a little space there that says that the general rule is this, and please write that rule there. Okay, looking at that rule just to kind of summarize it, basically to get U2, we had U1 plus 1 jump of D. To get to U3, we had U1 plus 2 jumps of D, right? To get to U4, we had U1 plus 2, 3 jumps of D. And to get to U5, we had U1 plus 2, 3, 4 jumps of D, right? So there's the summary again. So again, to get to any value, we do U1 plus 1 less than the term number jumps of D. Okay, that's our rule, key rule. I think we will stop here, and I'll have a second video ready for you that runs you through all the practice problems. So don't stop here. Make sure you go to that second video right after finishing here. See you soon.